Hey everybody, and welcome to another lecture in probability. Today we're going to be talking about multi-stage experiments. I don't know if I ever gave you this definition of an experiment or not. It's a horrible definition, but without using circular reasoning, it may not really be possible to get a better definition. As far as procedures and probability go, an experiment is a process that produces well-defined outcomes. Well-defined. Well, let's look at an example. I have a single die, and I toss it. There are exactly 6 possible outcomes. Face up on the die either turns out to be 1, 2, 3, 4, 5, or 6. This is the set of all possible outcomes. And as far as the outcomes being well defined, we could say that it's well defined in 2 senses. We don't have to look at the outcome of getting a 1 and saying, is this really an outcome? Or isn't it? It is an outcome. If we toss a single die, one of 6 things is going to happen, and this is one of those 6 things. As far as the outcomes being well defined, they're well defined in another sense too. We don't have to look at these 2 and say, are they really different outcomes or are they the same? 5 is a different outcome than 6. So each of these things, regardless of interpretation, is an outcome. And each of these things is a distinct outcome, different from all the others. Now let's look at another experiment. We toss a coin once. And barring the highly unlikely, it's not going to land on its side, okay? We just ignore that possibility. And it's not going to get away from us and roll down the street and fall into a sewer grate. We never know what happens. We toss a coin, and barring the highly improbable, one of 2 things will happen. Face up, the coin is either heads or it's tails. And again, these outcomes are well defined. We don't have to look at heads and say, well, is that really an outcome? Yes, it is. When we toss a coin, one of 2 things are going to happen, and this is one of them. It's also well defined in the sense that we don't have to look at these 2 things and say, are these really different outcomes or are they the same? Clearly, they're different outcomes. So an experiment is a process or a procedure that produces well-defined outcomes. Next, we want to look at the definition of something called a sample space. The sample space of an experiment is the set of all possible outcomes. Look at this experiment. Tossing a single die. Each of these outcomes, or each of these elements of the set, is an outcome of the experiment. Is this set missing any outcomes from the process of tossing a single die? No. If we toss a single die, exactly one of these 6 things is going to happen. So this is the sample space of the experiment where we toss a single die. Now, what about this experiment? We say that all of the possible outcomes are heads or tails. This is the set of all possible outcomes. So this is going to be the sample space of the experiment where we toss a coin. Okay? Now let's look at some related concepts. The next term that we'll look at is sample point. A sample point of an experiment is a distinct outcome of the sample space. And we've got a couple of examples that we can look at already. Suppose we perform the experiment of tossing a single die. The sample space are the values 1, 2, 3, 4, 5, 6. This is the sample space. One is a sample point. It's a distinct outcome of the sample space. So does that mean that 2 is also a sample point? It sure does. 2 is a sample point. 3? Certainly. 3 is a sample point, as are 4, 5, and 6. They are all sample points. So this experiment, which consists of tossing a single die, consists of 6 sample points. The sample space consists of 6 sample points. 1, 2, 3, 4, 5, 6. And if we toss a single die, our sample space consists of 2 outcomes, heads or tails. If we tossing a single coin, please forgive me. Tossing a single coin, exactly one of 2 things will happen. We'll either get heads. This is a distinct outcome. So getting heads is a sample point. Or we're going to get tails. Now we're about to define multi-stage experiment. Multi-stage experiment. Here we go. Multi-stage experiment. A procedure that consists of performing 2 or more experiments in succession is called a multi-stage experiment. And here's almost certainly the simplest example of a multi-stage experiment. Tossing a coin twice. The first stage of the experiment, we toss the coin the first time. The second stage of the experiment, tossing the coin the second time. And how many outcomes are there the first time? 2 outcomes. We either get heads or we get tails. And the second time we perform the experiment, two outcomes, heads or tails. For this multi-stage experiment, tossing a coin twice, there are four outcomes. Here's what can happen. The first time we toss the coin, we get heads. And the second time, we could get heads. That's one outcome. Or it could be the first time we toss the coin, we get heads. And the second time, we get tails. And these are the only possible outcomes if the first coin turns out to be heads. If the first toss gives us heads, then either the second toss gives us heads or it gives us tails. Those are the only two possibilities. But suppose we don't get heads on the first toss. Suppose we get tails. We get tails on the first toss. And if we get tails on the first toss, we might get heads on the second. Or if we get tails on the first toss, we might get tails on the second. The multi-stage experiment has four outcomes. We can either get heads on the first and heads on the second, heads on the first, tails on the second, or tails on the first, heads on the second, tails on the first, tails on the second. Those are the only possible outcomes. And notice something. The first stage had two possible outcomes. The second stage had two outcomes also. And the multi-stage experiment, tossing a coin twice, had four outcomes. Is that just coincidence, or is this always the case? And the fact of the matter is, it's always the case. I will repeat what I'm about to say over and over again, just to make sure that we don't miss it. But if we have a two-stage experiment, the number of outcomes for this two-stage experiment is going to be the number of outcomes of the first stage times the number of outcomes on the second stage. So it was no coincidence that this two-stage experiment had four outcomes. The number of outcomes had to equal the number of outcomes of the first stage times the number of outcomes of the second stage. Two outcomes times two outcomes, that gives us four outcomes. Well, I just got into this a couple of seconds ago. I might have done it prematurely, but since I've started the process, I might as well finish it. Namely, how do we know the number of outcomes of a multi-stage experiment? And in the experiment where we tossed a coin twice, it was the number of outcomes of the first stage times the number of outcomes of the second stage. And that's always the case with a two-stage experiment. The number of outcomes of a two-stage experiment is equal to the number of outcomes of the first stage times the number of outcomes of the second stage. And we can generalize this to the number of outcomes of a multi-stage experiment. The number of outcomes of a multi-stage experiment is the number of outcomes of the first stage times the number of outcomes of the second stage, times the number of outcomes of the last stage. That's how we compute the total number of outcomes of a multi-stage experiment. Now, these formulas are very good in the sense that they tell us how many possible outcomes there are for a multi-stage experiment. But what these formulas don't tell us is what each of these outcomes are. These formulas tell us the number of outcomes of a two-stage experiment, the number of outcomes of a multi-stage experiment, but these formulas don't tell us exactly what those outcomes are. And for that, we're going to have to use something called a tree. But before we do, let's just do a couple of examples using these formulas, okay? We've got the formulas up here. We might as well use them and make sure we know how to use them. So here's the first example. We toss a coin twice. The number of outcomes equals number of outcomes on the first stage when we toss the coin the first time, times number of outcomes in the second stage the first stage, there are two outcomes, either heads or tails. The second stage, there are two outcomes, either heads or tails. Okay, let's generalize this a little bit. Take a good look at that. I'm about to erase the example and do another one. We tweaked this example just a little bit. Here we're going to toss a coin 3 times. So now it's not just a two-stage experiment, it's a multi-stage experiment, more than 2 stages. And we'll use this formula. Number of outcomes of the multi-stage experiment, number of outcomes of the first stage times number of outcomes of the second stage, times the number of outcomes of the last stage. Number of outcomes of the first stage times number of outcomes of the second stage times number of outcomes of the third stage Well, each stage is exactly the same experiment as all the other stages. We're tossing a coin. And each stage has exactly 2 outcomes. So this is going to be 2 times 2 times 2, 8 possible outcomes. And that's good. We know how many outcomes there are. What this formula doesn't tell us is exactly what those outcomes are. We know how many, we don't know exactly what they are. This formula doesn't tell us. Well, let's do another example. We toss a coin 4 times. That's a 4-stage experiment. But the principle is still the same. We take number of outcomes on the first stage, number of outcomes on the second stage, times number of outcomes on the third stage, times number of outcomes on the fourth stage. And each stage is really the same as every other stage. We toss a coin. And there are 2 possible outcomes each time. 2 outcomes in the first stage, 2 outcomes in the second, 2 outcomes in the third, 2 outcomes in the fourth, 16 outcomes. I promise you, the next example will involve something other than coins. But just for the sake of how our problems are stated, here we tossed a coin 4 times. Is there any difference really in the experiment of taking a coin and tossing it 4 times and recording the outcome each time, or taking 4 coins and tossing them all at once? Is there anything really different about those experiments? Let's say that we have the coins marked. With an indelible magic marker, we write a little 1 on the first coin, and on the second coin we write a little 2, and on the third coin we write 3, and on the fourth coin we write 4. And we take those 4 coins and toss them. And we record the result of the first coin. We record the result of the second coin. We record the result of the third coin being tossed and the fourth coin. Is there any difference really in taking a coin and tossing it 4 times, or taking 4 coins and tossing them once? And to help us reason on this, let's say that I have 4 coins in my hand and I toss them. Are all of those 4 coins going to leave my hand at exactly the same split second? Probably one of those coins is going to leave my hand a little bit before the other coins. And of the 3 that are left, one of those is going to leave my hand slightly before the other 2, and so on. It's really the same experiment. Taking a coin and tossing it 4 times, no different than taking 4 coins and tossing them, 4 marked coins, 1, 2, 3, 4, and tossing them all at once. No difference. Now, the example I promised doesn't involve coins. Here it is. We have a single die, we're tossing it twice. So this is a 2-stage experiment, and the number of outcomes is going to be the number of outcomes of the first stage, the first toss, times the number of outcomes of the second stage, or the second time we toss the die. And we know each time we toss the die, there are 6 possible outcomes. So we have number of outcomes on the first toss times number of outcomes on the second toss. And each toss has 6 possible outcomes. "36 possible outcomes." Now I'm going to do the same thing that I did with the coins. I have a single die and I toss it twice. Is there any difference between that and taking a pair of dice and putting the number 1 on one of them and putting the number of 2 on the other, and taking those 2 dice and throwing them and recording the results for each one? And think about it. If I have a pair of dice in my hands and I toss them, one of those is actually going to leave it's going to leave my hand a little bit before the other one. Maybe 1/1000th of a second sooner. But it doesn't matter. That dice was thrown before the other. So if we toss a single die twice, that's the same as taking a pair of dice and tossing them once. 36 possible outcomes. One more like this, and then we will talk about trees. Here's the multi-stage experiment. We toss a coin, and then we toss a single die, a 2-stage experiment. So the number of outcomes of this 2-stage experiment will be the number of outcomes of the first, where we toss a coin, times the number of outcomes of the second, where we toss a single die. 12 possible outcomes. Now, as I mentioned earlier, these formulas are very handy. These 2 formulas are very handy because they tell us the total number of outcomes that we're going to have in a 2-stage experiment or a multi-stage experiment. But these formulas don't tell us what the outcomes will be. And for that, the device that we call a tree is very helpful. This is what we call a tree that models a multi-stage experiment. We start over here. This is the trunk of the tree. And for every outcome of the first stage, we have a branch. So in this case, I have 3 branches, which means that there are 3 outcomes of the first stage. And at the end of each of these branches, I have a node from which more branches sprout. But the first set of nodes represents the set of outcomes of the first stage. So this node, and this node represent all possible outcomes of the first stage of the experiment. Each of these branches that sprout from a node represent the outcomes of the second stage of the experiment. And given that the first stage ends in this outcome, we have 3 outcomes that represent we have three branches that represent three outcomes of the second stage. Given that the first experiment ends in this outcome, proceeding from this node, we have three branches that represent the same three outcomes of the second stage, and so forth and so on. Now, suppose that the tree ends right here. Suppose there are no branches sprouting any further. Then these nodes are actually the tips of the branches of the trees. These are the tips of the branches of the tree. And what do they represent? The tips of the branches represent the distinct outcomes of the multi-stage experiment. And each of the tips is a different outcome of this multi-stage experiment. And in this case, we only have two stages, so I guess it's a two-stage experiment. Having a tree is oftentimes a good way of accounting for every possible outcome of a multi-stage experiment. Let's take a look. Here we go. A coin is tossed 3 times, so it's going to be a 3-stage experiment. A coin is tossed 3 times. Draw a tree that gives all outcomes of the 3-stage experiment. Here's our trunk. And we either get heads or we get tails. And this is the first stage. Outcomes of the first stage. When we toss the second coin, we either get heads or tails again. These are the outcomes of the second stage. And then we toss a coin again, and there are 2 outcomes. 1, 2. 1, 2. 1, 2. 1, 2. This is the third stage. What does this tip represent? It represents getting heads on the first, heads on the second, heads on the third. So this is one outcome of our three-stage experiment. Heads, heads, heads. What about this tip? This represents the outcome of getting heads, heads, and tails. And this tip, this represents the outcome of the three-stage event in which we get heads, tails, and heads. And this tip represents getting heads, tails, and tails. This tip represents getting tails, heads, heads. This tip represents getting tails, heads, tails. And this tip, tails, tails, heads. And let's see. This tip, tails, tails, tails. Those are the outcomes of the three-stage experiment. And they're all equally likely. At every stage, the probability of getting tails or heads is exactly the same. This is our sample space for the three-stage experiment. These are the set of all distinct outcomes. And let's see, first stage had two outcomes, second stage had two outcomes, third stage had two outcomes, so we better have 2 times 2 times 2. We better have 8 outcomes here. 1, 2, 3, 4, 5, 6, 7, 8. Yep, there it is. Okay, we know what all of the outcomes are. We've accounted for all of them. Let's do a probability problem using the results that we got from this tree, okay? I'm going to leave the results up, but I'm going to erase the tree. This is a nice exercise. A coin is tossed 3 times, and here's our sample space. A coin is tossed 3 times. What is the probability of getting 3 heads? Okay, and remember, all of these outcomes are equally likely. Probability of 3 heads equals number of outcomes resulting in 3 heads over total number of outcomes. How many of these outcomes result in us getting 3 heads? Here's one. That's the only one, isn't it? So one outcome gives us 3 heads. And what's the total number of outcomes? 1, 2, 3, 4, 5, 6, 7, 8. So if we toss a coin 3 times, the probability of getting heads on every toss is 1/8. And that boils down to 1.25, I think. I'm sorry, boils down to 0.125. The probability of getting exactly one head, it will use the same formula. Number of outcomes resulting in exactly one head over total number of outcomes Okay, how many outcomes give us exactly one head? Here's one, here's one, here's one. Okay, so just three. This outcome gives us exactly one head. This outcome gives us exactly one head. This outcome gives us exactly one head. So 3, and total number of outcomes is 8. So the probability of getting exactly one head is 3 out of 8. And I guess that boils down to 0.0375. Now I should mention something. We took one coin here and tossed it 3 times. Suppose instead we took 3 coins and tossed them all at once. Would the experiment be any different? It's exactly the same thing as tossing one coin 3 times. Now let's look at another example. Another experiment. This one is 2-stage. A single die is tossed, and then a coin is tossed. First stage, 6 outcomes. Second stage, 2 outcomes. The total number of outcomes for this 2-stage experiment is going to be 6 times 2, 12 outcomes total. Let's draw the tree. Here's our trunk. And the first stage has 6 outcomes. And let's see, single die, okay, I'll write the number inside. 1, 2, 3, 4, 5, 6. This is the first stage. The second stage, a coin is tossed. 2 outcomes, heads, tails. Did I mess up? I'm sure I. Forgive me, please. Okay, heads, tails, heads, tails, heads, tails, heads, tails, heads, tails, heads, tails. Okay, this is our second stage. And here are the outcomes associated with that second stage. We have a 1 in heads, 1 in tails, 2 in heads, 2 in tails, 3 heads, 3 tails, 4 heads, 4 tails, 5 heads, 5 tails, 6 heads, 6 tails, first stage has 6 outcomes, second stage has 2. Number of outcomes of the first times number of outcomes of the second, 6 times 2 is 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. These are all of the outcomes. This is our sample space. One in heads, 1 in tails, 2 in heads, 2 in tails, and so forth. All of these outcomes make up the sample space of our 2-stage experiment. Now that we have the sample space, let's turn this into an exercise. Okay, we have the same sample space. We tossed a single, let's see, what did we do? We tossed a single die, and then we tossed a coin. And we want to know the probability of getting a 2 or less and tails. So the probability two or less and tails number of outcomes resulting in 2 or less and tails over total number of outcomes how can we get 2 or less? If we get 2 or less, we're either going to get a 1 or a 2. And we have to get tails. Well, this is 2 or less. And this is 2 or less. And they're both tails. So the number of outcomes resulting in 2 or less and tails is 2. Total number of outcomes is 12. So the probability is 1/6. Okay, probability of getting a 5 or greater. And that's the number of ways we can get a 5 or greater, or rather I should say total number of outcomes we can get a 5 or greater over the total number of outcomes. Number of outcomes giving a 5 or greater over total number of outcomes. Total number of outcomes is 12. And how many of these outcomes have a 5 or greater? all 4 of these, right? So the probability of getting a 5 or greater is 1/3. Maybe we have time for one more. Good example. We're going to do this one twice. We're going to do this one twice, I think. Let's see. Yeah, maybe we'll just do it once. A card is selected from a deck of cards. The card is replaced, and the deck is reshuffled. A second card is selected from the deck. In each case, only the suit of the card is observed: clubs, diamonds, hearts, or spades. And note that if I draw one card, there are 4 outcomes. It's either going to be clubs, diamonds, hearts, or spades. And they're all equally likely. There are 13 clubs, 13 diamonds, 13 hearts, 13 spades. So we start out with, there's 1, 2, 3, 4 outcomes. Clubs, diamonds, hearts, spades, this is our first set of outcomes. This is the first card. And then we put that card back in the deck, and the deck is reshuffled and shuffled and shuffled and shuffled. So again, every suit is equally likely. We put the first card that we drew back in the deck, so it's possible we could draw it again. There are going to be 13 clubs, 13 diamonds, 13 hearts, 13 spades. All suits are equally likely. Clubs, diamonds, hearts, spades. Clubs, diamonds, hearts, spades. And clubs, diamonds, hearts, spades. And finally, clubs, diamonds, hearts, spades. And we list the sample space. Club, 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 diamond, club, heart, club, spade, diamond, club, diamond, 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 heart, diamond, spade, heart, club, heart, diamond, heart, 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 spade, and then spade, club, spade, diamond, spade, heart, and spade, spade. And there are 4 outcomes of the first stage times 4 outcomes of the second stage. There should be 16 outcomes. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 16 outcomes. So it looks like we've done everything right. This is our sample space. And we'll remember that sample space and do a couple of problems based on this exercise. Okay, the first exercise that we're going to do using this example. Compute the probability that one of the cards drawn is a diamond and the other card drawn is a heart. And the probability of this event is the number of outcomes yielding diamond, number of outcomes yielding diamond and heart over total number of outcomes. The total number of outcomes, there were 4, 8, 12, 16 outcomes. Now, how many outcomes were such that one of the cards drawn was a diamond and the other was a heart? Well, here's one of them right here, a diamond and a heart. And here's another one, a heart and a diamond. And these are the only two places where we have both a diamond and a heart. So the probability that one of the cards drawn as a diamond and the other card drawn as a heart is 1/8. And I think that's 0.1275 or 0.125, something like that. Now let's do one more example using this experiment. This is a similar example, but it's not quite the same. Compute the probability that the first card drawn is a diamond and the second card drawn is a heart. So again, we're looking for the probability of getting a diamond and a heart, but the first card has to be a diamond and the second card has to be a heart. And if we look through all of the outcomes here, this is the only outcome where the first card is a diamond and the second card is a heart. The probability of that event is number of outcomes where the first card is a diamond and the second card is a heart. Let's see. First diamond, second heart, over total number of outcomes. The outcomes are still the same, 16. But here, the number of outcomes in which the first card is a diamond and the second card is a heart, just one, right here. So that's the probability. Now, there's something interesting about the way we did this example. We took a card from the deck, recorded the suit, and then we put the card back in the deck, shuffled the deck so that it was possible to draw that same card again. Probably we wouldn't draw that same card again, but it was possible. And essentially, the second card was drawn with replacement. That's the expression we use when we draw an item from a group of objects, record the value, and we put the object back in the group of objects so that it can be selected again. We say that the objects are drawn with replacement. And I will give that definition in just a second. Here's a concept that we need to know for probability exercises. Suppose that we are conducting a multi-stage experiment. Suppose also that each stage of the experiment consists of drawing a single object from a group of objects. For example, drawing a card from a deck of cards. We're drawing a single object. If the objects that are drawn during each stage of the experiment are returned to the group of objects so that they can possibly be drawn on the next stage of the experiment, then we say that the objects are drawn with replacement. And in the experiment that we just did, we drew a card, we recorded what the card was it a heart, diamond, spade, whatever, and then we put the card back in the deck and shuffled the deck and drew again. It was possible, although not likely, but it was possible that we might have drawn that same card again on the second draw. In the example that we just did, the card was drawn with replacement. We drew the card, we observed what the card was, we stuck the card back in the deck and we shuffled the deck again, and then we drew another card. Possibly the first card that we drew, but probably not. At any rate, when we drew the first card, we recorded it and we put it back in the deck and shuffled the deck. So it was possible to get that same card again. We drew that card with replacement. Here we have the dual to being drawn with replacement, and that is being drawn without replacement. Here's the definition. Suppose that we are conducting a multi-stage experiment. Suppose also that each stage of the experiment consists of drawing a single object from a group of objects. For example, drawing a card from a deck of cards. So far, everything is the same as before. If the objects that are drawn during each stage of the experiment are not returned to the group of objects after being drawn, then we say that the objects are drawn without replacement. And I'll use the example of drawing cards from a deck of cards again. Let's say that I draw two cards from a deck. I pick one card out of the deck, I look at it, and I put it in my shirt pocket, and then I draw a second card from the deck. Because that first card that I drew was put in my shirt pocket and not placed back in the deck, I can't possibly draw that same card again, no matter how much I shuffle the deck. And the thing is, when I took that first card and put it in my shirt pocket, I didn't replace it in the deck, did I? So I drew the second card without replacement. So if we're selecting objects from a group, and this is a multi-stage experiment, let's say I draw one object the first time and I put it in my pocket. I draw another object the second time, put it in my pocket. Draw another object the third time, put it in my pocket. Those objects are being drawn without replacement. Here's an experiment. A bag contains 4 balls, one red, one blue, one green, one black. 2 balls are drawn from the bag, one at a time, and are returned to the bag after being drawn. Well, if we replace each ball, or if we return each ball to the bag after being drawn, then this is with replacement, right? It's a 2-stage experiment. Let's draw the sample space. Here's our trunk. And in the first stage, we can do red, we can do blue, we can do green, or we can do black. And I'll have to denote black BL. This is the first stage. And keep in mind, after we draw the ball on the first stage, we return it to the bag so it can be drawn again. So in the second stage, I can draw a red ball, a blue ball, a green ball, a black ball, and after I've drawn a blue ball, I can draw a red ball, a blue ball, a green ball, and a black ball. You know, if I had any brains, I'd represent black as BK instead. BK for black. There we go. Red, blue, green, black. If I drew a green ball, my second ball can be red, blue, green, or black. And if the first ball I drew was black, I can draw red, blue, green, or black. And let's see. The first stage has 4 outcomes: red, blue, green, black. The second stage has 4 outcomes: red, blue, green, black. So there should be 16 sample points in our sample space, 4 times 4. This is red, 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 blue, red, green, red, black. This is blue, red, blue, 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 green, blue, black, green, red, green, blue, green, 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 black. And now the first one can be black, the second one blue, black, blue. Or it can be black, first one can be black, second one red, black, blue, oh, for crying out loud, forgive me, please. Black, red, black, blue, black, green, and black, black. And what do we have? 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Yep. 16 sample points in our sample space. Now let's do an example or two. Compute the probability of drawing a red ball and a green ball in any order. All of these outcomes are equally likely. The probability of that event is number of outcomes red and green, any order, over total number of outcomes. Number of outcomes where we have red and green. Here's one, a red ball and a green ball. And I think there's only one other, green ball and a red ball. So the number of outcomes that give us a red ball and a green ball in either order, 2. Total number of outcomes is 16. So the probability of drawing a red ball and a green ball in either order is 1/8 or 0.125, something like that. Now let's change this a little bit. This is similar to the last one. Whoops, this is part B, exercise B. Compute the probability of drawing a red ball first and a green ball second. Okay. Where does that happen? Red ball first? Well, these are the only four where the red ball is first, and this has green second. There's only one way that that happens. Probability of this happening, number of outcomes, red first, green second, over total number of outcomes. Number of outcomes, red first, green second, just one, there it is. Total number of outcomes, 16. So the probability of that happening, getting red first and green second, 1/16. Now I'm going to do something like this again, but it's going to be different. A bag contains 4 balls. This time I'm not going to use 2 different colors that start with the same letter. The balls are red, blue, green, yellow. 2 balls are drawn from the bag in succession without replacement. So when we pick the first ball out of the bag and look at it and record the color, we don't put the ball back in the bag with the other balls. We take that first ball that we selected, we observe the color, and then we put it in our pocket. And we select the second ball without having replaced the first. So this drawing is done without replacement. Let's draw the sample space. Here's our trunk. And we have red, blue, green, and yellow. This is the first stage of our experiment. We've drawn 1 ball, and we're drawing it without replacement. We draw a second ball. And what colors can the second ball be? So you say red, blue, green, yellow. Is that right? If I drew the first ball without replacement, I'm not going to put it back in the bag, am I? So there's no way that the second ball that I draw can be red. That can't happen. If I drew the red ball on the first draw, I can't draw it on the second draw. So there are only 3 options on the second draw. I can either get blue, green, or yellow. Now suppose the second ball is blue. And suppose the first ball that I draw is blue. Can my second ball be blue also? It can't be, can it? Because I already drew the first ball and it was blue, and I put that blue ball in my pocket. I can't draw it again. So my options are red, green, and yellow for the second ball. Suppose the first ball was green. I can't draw a green ball the second time because I never replaced the green ball the first time. So I can draw a red ball, a blue ball, or a yellow ball. 1, 2, 3. And suppose the first ball I draw is yellow. Then the second ball that I draw can't be yellow. It will either be red, blue, or green. And this is my sample space. I can get red and blue. I can get red and green. I can get red and yellow. I can get blue and red, blue and green, blue and yellow, I can get green and red, I can get green and blue, I can get green and yellow. Or I can get yellow and red, yellow and blue, yellow and green. Okay, these are my outcomes. This is my sample space. Let's do an example or two. First example, compute the probability that the balls are red and blue in either order. Okay, the probability of this event occurring. Number of ways we can get red. See, number of outcomes. Where we have red and blue, either order, over total number of outcomes. How many outcomes give us red and blue? This one does. And this one does. Then that's it, isn't it? 2 outcomes give us red and blue. What are the total number of outcomes? Let's see. 4 outcomes in the first stage. In the second stage, only 3 outcomes. 4 times 3 is 12. Does that work? Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yes, 12 outcomes. So here the probability is 1/6 of getting a certain pair of balls in either order. When we did it before with replacement, the probability was 1 out of 8, wasn't it? So if we have an experiment where things are drawn without replacement, it makes a big difference. It changes the probabilities. Now, one last variation of this, let's do it. Compute the probability that the first ball is red and the second ball is blue. So the probability of this event equals number of outcomes with red first and blue second, all over total number of outcomes. And remember, because we drew without replacement, we only have 12 outcomes. And how many of these outcomes if red is the first ball and blue is the second? Well, these are the only 3 outcomes that have red as the first ball, and this is the only outcome that has blue as the second. There's only one way that we can draw red on the first and blue on the second. So the probability that we draw red on the first and blue on the second, 1/12. Next time, we'll expand our repertoire of probability exercises. We'll do and or probability.